Imagine you're sitting in a room right now.
Right.
Just take a look around. Chances are you can look out and there's this completely invisible barrier standing between you and the world outside.
Yeah, absolutely.
And you probably haven't thought twice about it today, or I mean, maybe even this entire year. We just expect it to let the light in perfectly, to keep the freezing cold or the sweltering heat out, and to stay flawlessly transparent.
He's just there.
Exactly. It is an absolute marvel of modern chemistry and engineering, and yet we treat it like empty space. We literally just look right past it.
It really is kind of the ultimate paradox of the material world. I mean, we demand that it be perfectly invisible to our eyes, yet structurally flawless enough to hold up soaring skyscrapers.
Right.
It has to protect us from hurricane-force winds, insulate our homes against wild temperature swings. And the thing is, when it fails dramatically. But when it works, which is honestly almost all the time, it gets zero credit.
Zero credit. And that is exactly what we are fixing today. So welcome to this custom deep dive designed specifically for you. We are pulling back the curtain, well, looking right through the pane at the vast, incredible, and super complex world of glass.
It's a massive topic.
It really is. And
Yeah.
we have a brilliant stack of materials driving this conversation today. We're drawing heavily from a comprehensive glass industry crash course from the CM Tech Institute.
Right, which really breaks down the foundational science.
Exactly. We are also integrating forward-looking data from the Glass Manufacturing Industry Council's 2026 report, along with some highly technical, cutting-edge architectural insights from the engineering teams at Tough Glaze and Onoplast.
It's a really powerful combination of sources, honestly. The CM Tech material grounds us in the reality of how this stuff is actually forged, while the GMIC and architectural reports show us, like, where the absolute limits of the technology are being pushed right now.
Yeah, it's wild. So the mission for this deep dive is simple but ambitious. We want to take you from simply looking through glass to truly understanding the science, the manufacturing, and the crazy futuristic potential of this essential material. So, okay, let's unpack this.
Let's do it.
Because what seems like a simple, fragile pane of window glass is actually a masterclass in chemistry, thermodynamics, and extreme engineering. So let's start at the very beginning. The foundational question.
What is glass?
Right. What exactly is glass? Because it's not quite a solid in the traditional sense, right? I mean, I remember hearing somewhere that it's actually a super cooled liquid that flows over centuries, and like that's why old church windows are thicker at the bottom.
I am so glad you brought that up.
Oh, really? Is that wrong?
We need to kill that myth immediately.
Oh, wow. Okay.
Yeah, that is a massive misconception. Old church windows are thicker at the bottom just because medieval glass-making techniques were, well, imprecise.
So it's just bad manufacturing.
Basically, yeah. They spun molten glass into these flat discs, which naturally have thicker edges. And glaziers intuitively installed the heavier, thicker side at the bottom for stability. It has absolutely nothing to do with the glass flowing over time.
That makes so much more sense.
Right. At room temperature, glass does not flow. It is entirely solid. But, and this is a really crucial but, it is what we call an amorphous solid.
Okay, an amorphous solid. Break that down for me. If I look at a chunk of iron or a diamond or a grain of salt under a super powerful microscope, what am I seeing that I don't see in glass?
So if you look at most solid materials like metals or crystals, their atoms are arranged in a highly organized, repeating, rigid lattice structure.
Like a grid.
Exactly. They form predictable geometric patterns. Think of a crystalline material like a marching band.
Oh, right. Perfectly aligned. Every atom in exact formation, marching in step, predictable spacing between every single member.
Precisely.
Yeah.
But glass doesn't do that. It is non-crystalline. So if you use your analogy, the amorphous structure of glass is more like a disorganized, chaotic dance floor that just suddenly got frozen in time.
Frozen in time. I love that.
Yeah, everyone is just stopped exactly where they were, facing different directions, totally random distances apart. There is no long-range order to the atomic structure at all.
That is a fantastic way to visualize it. And if I'm understanding the CM Tech crash course correctly, that frozen random arrangement is exactly what gives glass its unique cocktail of properties, right?
Exactly.
Because there are no internal grain boundaries or neat crystalline planes for light to bounce off of or scatter against, the light waves just pass right through the gaps in the chaotic dance floor.
Yeah, they just zip right through it.
And that's why it's transparent.
That is the optical benefit, yes.
Yeah.
But that same disorganized structure is also why it behaves the way it does physically.
Yeah.
It is incredibly hard, but notoriously brittle.
Right. It shatters.
Right. because there are no organized planes for the atoms to slide past one another, like they can in metals when you bend them. Glass just can't absorb energy by deforming. It just holds the stress until the molecular bonds are completely overwhelmed, and then it catastrophically snaps.
So to make this frozen dance floor, you need the right ingredients and a whole lot of heat. According to the crash course, the most common type of glass we interact with, which makes up about 90% of all glass produced globally, the stuff in our windows and bottles, is called soda lime glass. Let's walk through that recipe.
Sure. So the primary ingredient, the absolute backbone of the entire structure, makes up about 70% of the batch. And this is silicon dioxide.
Which is basically sand, right?
Essentially, yes.
Yeah.
Pure silica sand. That is your main glass-forming compound. If you could somehow melt that on its own, you get fused quartz, which is incredibly pure and strong.
But you can't just throw sand in your oven at home and make a window.
Far from it. Pure silica has a staggeringly high melting point. We're talking around 1,700 degrees Celsius, or over 3,000 degrees Fahrenheit.
Oh, wow.
Yeah. Building and maintaining industrial furnaces that can continuously run at that temperature is, frankly, astronomically expensive and incredibly difficult from an engineering standpoint. The refractory bricks lining the furnace would just melt or degrade way too quickly.
So the industry had to find a cheat code, a way to get the sand to melt without needing the temperature of a small star.
Precisely. And to make it viable for mass industrial manufacturing, we introduced the second major ingredient, which is sodium oxide. In the industry, they use soda ash for this.
Soda ash, okay.
Right. It makes up about 15% of the raw mixture. And the soda ash acts as a flux.
A flux, like in soldering.
Very similar concept, yeah.
Okay.
A flux dramatically lowers the melting point of the primary material. By introducing the sodium, it disrupts those tight silicon-oxygen bonds in the sand. So it forces the sand to melt at a much more manageable 1,500 degrees Celsius.
Which is still insanely hot, but better.
Exactly. This single addition saves a massive amount of energy, literally millions of dollars in fuel, and saves the furnace itself from burning out prematurely.
But there's a catch, isn't there? Because the CM Tech Guide highlights a major chemical flaw if you just stop right there. If you just mix sand and soda ash, you get a glass called sodium silicate. And sodium silicate has a rather, embarrassing property for a building material.
Yes, it does.
It is water soluble. It literally dissolves in water.
It does. It's often called water glass in the industry.
Yeah.
If you built a house with windows made only of sand and soda ash the very first time it rained, your windows would turn into a sticky syrup and just slide down the side of your house.
Which is obviously terrible for a window.
Which is why the third major component is absolutely vital, and that is calcium oxide provided by limestone.
Okay, limestone.
Right. Limestone makes up about 9% of the mixture, and it acts as a chemical stabilizer.
Mm-hmm.
It bonds with the silica and sodium network and locks it firmly in place, giving the glass its chemical durability and water resistance.
So it waterproofs it.
Exactly. It ensures the glass doesn't melt in the rain or degrade when you wash it.
So sand for the structure, soda ash to lower the melting point, limestone to make it waterproof, throw in some minor additives, maybe some aluminum oxide for extra durability, or magnesium oxide to prevent the glass from crystallizing while it cools. And you have your raw materials, your batch, ready to go.
And that brings us to the actual manufacturing floor. How we take this pile of powdery rocks and turn it into the flawless, perfectly flat, optically clear windows we use every single day.
This is a process that absolutely fascinated me when I was going through the materials, the float glass process.
It's incredible.
According to the industry data, it was invented by Sir Alistair Pilkington in 1959, and over 90% of all flat glass is made this way today. But before we get into how it works, paint a picture for me of what the industry looked like before 1959, because it sounds like a total nightmare.
Oh, it was incredibly laborious. Before Pilkington, if you wanted a flat, clear piece of glass for a mirror or a large window, you had to use the plate glass method. You literally poured molten glass onto a large iron casting table and rolled it out with a heavy iron cylinder.
Kind of like rolling out dough for a pie.
Exactly like that.
Yeah.
But obviously that wouldn't be perfectly smooth. The iron table would leave marks, the roller would leave marks.
Right.
So the glass would be thick, cloudy, and completely distorted on both surfaces. To make it transparent, you had to physically grind and polish both sides of the glass ribbon using massive rotating cast iron discs and abrasive slurries like sand and water, and eventually rouge for the final polish.
That sounds miserable.
It was incredibly slow, heavily reliant on manual labor, generated massive amounts of waste, and made high-quality glass staggeringly expensive.
And then Pilkington comes along and just finds a way to let physics do all the hard work. He figured out a way to completely eliminate the mechanical grinding and polishing.
He did.
So picture this. You're at the plant. You take that mixture of sand, soda ash, limestone, and you also add something called cullet, which we'll definitely talk more about later, but it's basically recycled glass of the exact same chemical recipe.
Right.
You feed this massive batch into a continuously running furnace. You heat it to that unimaginable 1,500 degrees Celsius, over 2,700 degrees Fahrenheit. It cooks into this glowing, molten, incredibly viscous, syrupy liquid. And then, and this is the crazy part, it flows out of the furnace and is poured directly onto a bath of molten metal.
What's fascinating here is the specific choice of metal for that bath. The glass industry settled on molten tin. Now, why use a liquid metal, and why tin specifically?
Well, let's break it down. Why does the glass float on it in the first place? Like, if I pour a 1,500-degree liquid rock onto a liquid metal, why don't they just mix together into some toxic, unusable soup?
It all comes down to specific gravity, or density. Molten glass is significantly less dense than molten tin. Furthermore, molten glass and molten tin are immiscible, meaning they chemically do not want to mix.
Much like oil and water.
Exactly like oil and water. So when the liquid glass pours onto the liquid tin, it stays entirely on the surface. It just floats.
Okay, so it floats, but why tin? Why not, I don't know, lead or iron or aluminum?
Tin has a very unique set of physical properties that make it the perfect and honestly perhaps only candidate for this job. First, it has a low melting point, around 232 degrees Celsius, but a very high boiling point, over 2,600 degrees Celsius.
So at the 1,100 degrees where the glass is pouring onto it, the tin is comfortably liquid, but it's nowhere near boiling.
Right.
So it isn't bubbling or creating vapors that would pit or ruin the bottom of the glass?
Exactly. It provides a perfectly calm, perfectly level, mirror-smooth liquid surface. And because the glass is floating on this perfectly level liquid, the bottom of the glass spreads out and becomes flawlessly flat.
That's genius.
And at the same time, gravity and surface tension pull the top surface of the molten glass, making it perfectly flat and parallel to the bottom. It forms a ribbon of uniform thickness with pristine optical clarity. No mechanical grinding or polishing required. Ever.
It's brilliant. It's essentially an endless conveyor belt made of liquid mirror.
It completely revolutionized architecture. Suddenly, massive, optically perfect panes of glass were affordable to produce at industrial scale.
But as it flows down this tin bath, it has to be cooling down, right? I mean, you can't just keep it at 1,100 degrees forever.
Right. The tin bath is enclosed in a massive chamber with a highly controlled atmosphere of nitrogen and hydrogen to prevent the tin from oxidizing. And as the glass ribbon floats along this bath, the temperature is gradually reduced from roughly 1,100 degrees down to about 600 degrees Celsius by the time it reaches the end of the bath.
And at 600 degrees, it's still incredibly hot, but it's transitioned from a syrupy liquid into a solid ribbon. It's rigid enough to be touched without deforming.
Precisely. At the exit of the tin bath, large mechanical rollers actually lift the rigid glass ribbon off the tin and pull it forward onto a standard roller conveyor. And here's another piece of engineering brilliance. The speed of those specific pull rollers is what actually determines the thickness of the final glass.
Wait, really? They don't have, like, a mold or a squeegee system dictating the thickness?
No molds at all.
Yeah.
If you want thin glass, say for a picture frame, you just speed up the rollers. They pull the glass faster than it's pouring into the bath, stretching the molten puddle thinner before it solidifies.
Wow.
And if you want thick glass, for a heavy tabletop, you slow the rollers down. The molten glass pools up and spreads out to its natural equilibrium thickness, which is about 6.8 millimeters. Or you can even use mechanical guides on the edges called top rollers to push it thicker.
That is deeply elegant. But wait, I want to clarify something the CM Tech guide mentioned. Because the glass was literally floating on liquid metal, the two sides of the glass aren't actually identical chemically, right? Even though if I hold up a piece of standard window glass, both sides look perfectly clear and identical to me.
That is a critical point for the downstream processing of glass. The process leaves the glass with what manufacturers and fabricators call a tin side and an air side.
Right.
The bottom of the glass, the side that was physically touching the molten tin, absorbs microscopic amounts of tin into its atomic structure during the journey down the bath.
Does that affect how we use it day to day?
To the naked eye looking through a window, no. It looks exactly the same. But for fabricators who are later applying highly sensitive, low-emissivity thin film coatings, or doing silvering to make mirrors, or even certain types of digital ceramic printing, knowing which side is the tin side is absolutely crucial.
Why? What happens?
The microscopic tin contamination changes how chemicals react with the surface. If you try to apply a delicate coating to the tin side, it might fail, peel, or just look hazy. Manufacturers actually use special UV light wands in the factory to detect the tin side under UV. The tin side glows with a faint, milky fluorescence.
That is so cool. Okay, so our continuous ribbon of glass has come off the tin bath. It's 600 degrees Celsius. It's rigid. Can we just run it out into the factory, let the room temperature air hit it, and chop it up into windows?
Absolutely not.
Oh, okay.
If you exposed 600-degree glass to standard room temperature air, it would undergo catastrophic thermal shock.
Like a shatter.
Violently. The outside surfaces would cool and shrink rapidly while the inside remained hot and expanded. The internal stresses would tear the material apart, and the entire ribbon would explode into a million pieces on the conveyor belt.
Which would be a very bad day at the factory. So how do they cool it without blowing it up?
It enters a critical piece of equipment called an annealing layer.
An annealing layer. Okay, unpack that for me.
An annealing layer is essentially a highly controlled, incredibly long cooling oven. We are talking a tunnel that can be over 100 meters long. The glass ribbon travels continuously through this tunnel on rollers. The temperature inside the layer is strictly managed, creating a very precise thermal gradient.
So it steps it down slowly.
Right. It slowly, meticulously drops the temperature of the glass from 600 degrees Celsius down to room temperature over a specific duration of time.
What does that slow cooling actually do on a molecular level? Why is it different than just letting it sit in a room?
The slow, controlled cooling, the annealing, allows the temperature of the glass to remain uniform all the way through its thickness as it drops. This ensures that the entire piece of glass shrinks at the exact same rate.
Got it.
This process relieves all the internal thermodynamic stresses that built up during the rapid transition from liquid to solid. It essentially relaxes the atomic structure.
And when it finally emerges from the other end of the layer, what they call the cold end, automated machines equipped with carbide scoring wheels cut this continuous miles-long ribbon into massive sheets, often 10 feet by 17 feet, to be stacked and shipped.
Exactly.
And what you have at that point is basic, standard, annealed float glass. It is perfectly flat, it has flawless optical clarity, it is completely free of internal stress. But as the CM Tech crash course makes very clear, it has one massive, potentially lethal flaw.
Yes, it absolutely does. Annealed glass has a baseline tensile strength of about 6,000 pounds per square inch, or SIAS.
Which sounds like a lot.
It might sound like a lot, but in the context of building materials, it's quite low.
Yeah.
If you impact standard annealed glass with enough force, a baseball, a strong gust of wind, or a person falling against it, it breaks. And when it breaks into large, heavy, jagged, incredibly sharp shards, like daggers or guillotines.
From a safety perspective, using that in a door or a shower enclosure or a car window is entirely unacceptable. The liability and the danger are just off the charts.
Exactly. Building codes globally have universally banned the use of standard annealed glass in what are considered hazardous locations: doors, windows near the floor, bathrooms, overhead glazing. If a human being can reasonably accidentally impact the glass, it cannot be standard annealed.
Which brings us perfectly into the next phase of our journey, the glass spectrum, moving from these standard dangerous panes to the world of super strength safety glass. Because we obviously still use glass indoors and showers. So how do we fix this fatal flaw? How do we make glass safe?
We have to process it further. We have to take that perfectly relaxed annealed glass and intentionally introduce immense, highly controlled stress back into it.
Stress.
Yes, and we do that by manipulating its thermodynamics using heat. The first step up the strength ladder is what we call heat-strengthened glass.
Walk me through that. What are we doing differently?
You take that standard annealed glass, cut it to its final size, run the edges through a grinding machine so they are smooth, and then you send it into a tempering furnace. You heat the glass up again, right to its softening point, around 620 to 650 degrees Celsius, and then you cool it down.
Okay, so reheating and cooling.
But you cool it much faster than the annealing process, using forced air.
By cooling it faster, you're trying to trap some stress in there.
Precisely. You create a moderate amount of surface compression. This makes the glass about twice as strong as standard annealed glass, hitting roughly 12,000 psi in surface compression strength. It can withstand significantly higher wind loads and thermal stresses.
But, and this is a big but, that the structural engineers listening will know heat-strengthened glass is still not legally classified as safety glass.
No, it's not.
Why not? If it's twice as strong, shouldn't it be safe?
Because strength is only half the equation for safety glass. The other half is the break pattern. How does the material behave when it fails?
Ah, right.
If you hit heat-strengthened glass hard enough to break it, it still breaks into relatively large sharp pieces. They are slightly smaller than annealed glass shards, but they are absolutely still capable of causing severe lacerations. So, while heat-strengthened glass is fantastic for the upper floors of skyscrapers, where you need to resist high wind loads but don't want the glass to fall out of the frame if it cracks, it is not a human safety glass.
So if you want true safety glass, you have to go all the way. You have to go to full tempered or toughened glass. And the physics behind the tempering process, this is where my jaw dropped when reading the CM Tech materials. It is a wildly counterintuitive process.
It really is.
You heat the glass to over 600 degrees Celsius, over 1100 degrees Fahrenheit, until it is practically glowing and on the verge of sagging.
Yeah.
And then you don't just cool it slowly, and you don't just use a moderate fan. You plunge it between massive arrays of high-pressure air jets. You violently blast it with cold air.
Yes, it is known as the quench.
No, wait, hold on. We just established, like 10 minutes ago, that if you hit 600-degree glass with room temperature air, it explodes from thermal shock. Why does this high-pressure air blast not instantly shatter the glass into dust? What is the secret here?
That is the exact logical assumption, and it is why perfecting the tempering process took decades of engineering. The secret is the speed, the absolute uniformity of the air blast, and the physics of how glass cools.
Okay, break it down.
When you blast that hot glass with high-pressure ambient air simultaneously on both sides, the outer surfaces of the glass, the skins cool down and solidify almost instantaneously. They just freeze in place.
Okay, so the outer skin is solid, but the middle of the glass.
The inner core of the glass, the meat of the sandwich, is insulated by those outer layers. So the core is still 600 degrees, still hot, and still somewhat viscous. Now, here's where the magic happens. As that inner core eventually begins to cool down over the next few seconds, basic thermodynamics dictates that it must contract. It wants to shrink.
But the outer skin has already solidified. It can't shrink anymore.
Exactly. The solid outer layers absolutely refuse to move. So as the hot core cools and tries to shrink, it violently pulls inward on those already solidified outer surfaces.
You create a massive, permanent, internal molecular tug-of-war.
Precisely. You create a state of immense surface compression. The outer skins of the glass are being crushed inward by the core, while the core itself remains locked in a state of permanent tension, constantly pulling. The surface compression achieved in fully tempered glass is enormous, greater than 10,000 psi.
Let's contextualize 10,000 psi for the listener, because that is not a trivial number. That is the equivalent of stacking a fully grown African elephant balancing on a stiletto heel onto a single square inch of the glass surface.
It is an incredible amount of stored energy. And the reason this makes the glass so strong is a fundamental rule of material science. Glass practically only ever fails under tension. It almost never fails under compression.
Interesting.
Yeah, when you hit a piece of glass, the side you hit goes into compression, but the opposite side stretches and goes into tension. If the tension exceeds the strength of the molecular bonds, a crack forms and the glass breaks.
Ah. So because the tempering process has preloaded the surfaces with 10,000 psi of compression, any physical impact, a baseball, a hammer, has to first overcome that 10,000 psi of compression before the glass even reaches a neutral state, let alone goes into the tension required to break it.
Exactly. It acts as an invisible armor.
Which makes tempered glass 4 to 5 times stronger than standard annealed glass.
But the strength isn't even the best part. The best part is the safety feature. If you do manage to hit it hard enough, say with a pointed object like a center punch, that pierces that compression layer and reaches the tension core, the whole tug-of-war system catastrophically fails.
All that stored 10,000 psi of energy is released violently, all at once. The crack propagates through the entire pane of glass at roughly 3,000 miles per hour. The glass completely shatters into thousands of tiny, relatively harmless, cube-shaped pieces. The industry calls it a dice pattern.
It is a phenomenal life-saving safety feature. If you slip and fall against a tempered glass shower door, the glass will explode into those cubes. You might get a few minor scratches or a fright from the loud pop, but you will not face lethal guillotine-like shards. You will survive.
It's brilliant, but I have to ask a naive question here. If tempered glass is so incredibly strong and when it finally breaks is basically harmless, why don't we just use it for absolutely everything? Why isn't the windshield of my car made of tempered glass? It seems like a no-brainer.
If we connect this back to the bigger picture of how a vehicle actually operates in the real world, you'll see the catastrophic problem with that idea immediately.
Oh.
Imagine you were driving your family down the highway at 70 miles per hour. A semi-truck ahead of you kicks up a sharp piece of gravel. It hits your tempered windshield right in the center. The point of the rock pierces the compression layer. What happens?
Well, the tug-of-war fails. The entire windshield instantly shatters into thousands of tiny, opaque cubes.
And suddenly, you are driving completely blind at highway speeds. You cannot see the road, the cars around you, or the barriers. Furthermore, because there is no structural integrity left, the wind pressure instantly blows all those thousands of glass cubes directly into your face and your lap at 70 miles an hour.
Oh, right. That is a terrifying scenario. Okay, so for a windshield, we absolutely do not want it shattering into tiny pieces. We need it to break, absorb the impact, but stay exactly where it is so we can still see and still be protected from the wind.
Exactly. For car windshields, for overhead skylights in a mall, or for blast-resistant high-security areas, we need a different kind of safety glass. We need laminated glass.
Laminated glass. This is essentially the heavy-duty sandwich of the glass world. Walk me through the construction.
So you take two panes of glass. They can be standard annealed, heat strengthened, or even tempered, depending on the engineering requirements. And you bond them together using a heavy-duty, highly durable plastic inner layer. The most common material used historically and today is polyvinyl butyrol, or PVB.
PVB, got it.
For high structural applications, they use ionoplast inner layers, commonly known by the trade name Sentry Glass. The standard thickness for a typical commercial laminate usually runs about 6.38 millimeters or 10.38 millimeters in total.
They lay the sandwich up in a clean room, vacuum out the air between the layers, and then bake it in a massive pressure cooker called an autoclave to permanently fuse the glass and the plastic into a single optical unit.
That's the process.
And the brilliance here is purely mechanical. If that same rock hits a laminated windshield at 70 miles per hour, the outer layer of glass will crack. It might spiderweb terribly.
But those sharp glass shards have nowhere to go. They adhere fiercely, molecularly, to that tough PVB plastic core. The plastic stretches slightly to absorb the kinetic energy of the impact, preventing the rock from entering the cabin. The inner pane of glass often remains completely intact.
That's amazing.
Yeah, the windshield stays in the frame, the structure of the car's cabin is preserved, and most importantly, you maintain visibility to safely pull over.
And what's amazing is that once you introduce this plastic inner layer, you unlock a whole suite of side benefits that engineers utilize constantly. For example, that PVB interlayer naturally blocks over 99% of harmful ultraviolet, or UV, rays, protecting your skin and preventing the dashboard and upholstery from fighting.
It is also a phenomenal acoustic dampener.
Really?
Oh yeah, the plastic core interrupts sound waves much more effectively than a solid piece of glass. If you've ever been in a hotel near an airport and noticed how eerily quiet the room is, chances are the windows are thick laminated glass designed specifically for acoustic protection.
And if we look at areas like Miami or the Gulf Coast, laminated glass is the backbone of hurricane defense. If you build the glass panes and the Sentry Glass interlayer thick enough, it can literally stop a hurricane-blown 2x4 timber traveling at 50 feet per second from breaching the envelope of a house.
It's practically bulletproof in that context.
It takes the hit, cracks, but does not yield. If a window blows out in a hurricane, the sudden pressurization of the house can literally lift the roof off. Laminated glass prevents that catastrophic failure.
It is an indispensable architectural tool. But we shouldn't limit our understanding of glass chemistry strictly to the soda-lime standard we've been discussing. While soda-lime is the workhorse of the industry, there are specialty chemical compositions designed specifically for extreme environments where standard glass would immediately fail. Take borosilicate glass, for example, widely known to consumers by the brand name Pyrex.
Right. The CM Tech Guide notes this one has a high amount of boric oxide added to the silica sand instead of so much soda ash. And the superpower of borosilicate glass is that it has an incredibly low thermal expansion coefficient. Let's explain why that matters.
Almost all solid materials expand when they are heated and shrink when they are cooled. It is basic kinetic energy. The atoms vibrate more and take up more space. If you take a standard soda lime glass jar out of the freezer and immediately pour boiling water into it, you are going to have a bad day.
Because it expands too fast.
Exactly. The inside surface of the glass rapidly heats up and aggressively tries to expand. But glass is a poor conductor of heat, so the outside surface is still freezing cold and refuses to expand.
The inside is pushing, the outside is holding firm, and the massive internal stress rips the glass apart. It shatters instantly.
Borosilicate glass solves this chemistry problem.
Okay, stop right there. Why 400 degrees? Why molten salt?
The 400-degree temperature is highly strategic. It is hot enough to make the atomic lattice of the glass just pliable enough to allow movement, but not hot enough to actually melt the glass or relieve all its structural tension. Now, in the chemical structure of the aluminosilicate glass, you naturally have sodium ions distributed throughout. But in the molten salt bath, you have an overwhelming concentration of potassium ions.
And here is the crucial physical detail. Potassium ions are physically, dimensionally larger than sodium ions.
Exactly. So basic diffusion takes over. The heat allows the smaller sodium ions to vibrate out of their positions in the glass and dissolve into the salt bath. And because nature abhors an imbalance, the larger potassium ions from the bath force their way into the microscopic cavities left behind in the surface of the glass.
I love the analogy we used earlier for this. It's like taking a wooden bookshelf that is already completely tightly packed end to end with small paperback novels. You pull out the paperbacks one by one and you forcefully, aggressively jam massive, thick, hardcover encyclopedias into those exact same slots.
That is a perfect visualization. You are literally stuffing larger atoms into a space meant for smaller ones. Because the glass cools down and the atomic lattice locks back into place, those massive potassium ions are trapped. They physically wedge the surface of the glass incredibly tight.
Creating compression again.
Yes, this creates a deeply compressed, incredibly dense armor-like surface layer at the atomic level. It makes the screen highly resistant to the scratches of keys in your pocket and gives it the flexibility and impact resistance to survive a drop onto concrete.
Okay, so we've covered the actual material of the glass itself, how the chemistry works, how the float process makes it flat, how tempering makes it strong, and the wild specialty recipes like ion exchange. But a modern window in a commercial building or a new home isn't just a single piece of glass anymore. That would be an energy disaster. It is a highly engineered, multi-component system. This brings us to the architecture of the window and the invisible, absolute magic of the gases inside.
Right. If you talk to an architect or a glazier, they don't really call them windows anymore. They refer to them as insulated glass units, or IGUs. And the construction, the precise engineering of an IGU, is the single most critical factor in the energy efficiency of any modern building envelope.
Right. An IGU is essentially a sealed, transparent thermos. You have 2 panes of glass, or 3 if you're in a really extreme climate, separated by a spacer around the perimeter edges. Historically, for decades, those spacers were made of hollow aluminum tubes.
Which is a terrible idea.
Because aluminum is a highly conductive metal, it conducts heat brilliantly. If it is freezing outside, an aluminum spacer will act as a thermal bridge, pulling the freezing cold directly from the exterior pane through the spacer and right onto the interior pane of your living room.
Which leads to a cascade of building failures. The interior edge of the window gets freezing cold. The warm, relatively humid air inside your house hits that cold edge, and the moisture instantly condenses. You get water pooling on your windowsills, which leads to mold, rot, and massive energy loss as your heating system fights a losing battle against the thermal bridge.
That's why the modern industry completely moved away from aluminum and adopted warm-edge spacers. These are made of composite plastics, silicone foams, or highly engineered stainless steel with massive thermal breaks. They physically stop the heat or cold from traveling around the edge of the glass. But the spacer isn't just a structural separator. It has a hidden job. Inside that hollow spacer tube, there is a material called a desiccant.
A desiccant is a molecular sieve, a highly aggressive moisture-absorbing material. Similar to those little do-not-eat silica packets you find in shoeboxes, but on an industrial scale. When the IGU is manufactured, a tiny amount of ambient moisture is inevitably trapped in the airspace between the panes. The desiccant absorbs every single microscopic molecule of that water. It ensures that the air inside the window is bone dry, meaning the inside of your window will never, ever fog up, no matter how cold it gets outside.
And to keep that dry air in and the wet weather out, they have to seal the absolute life out of this sandwich. They use a highly specific dual sealant system. The primary seal, applied directly between the glass and the side of the spacer, is polyisobutylene, or PIB. It is a black, sticky, incredibly dense rubber that acts as an impermeable barrier. It stops moisture from getting in and it stops the special gases inside from leaking out.
But PIB has very little structural strength. It can't hold the heavy glass panes together. So they apply a secondary seal around the outside edge of the spacer. This is usually a heavy-duty structural silicone or polyurethane. This secondary seal acts as the glue. It cures into a tough rubber that physically holds the entire heavy glass sandwich together against wind loads and barometric pressure changes.
But the spacer and the seals are just the frame. It's what they put inside the sandwich, in that gap between the glass that truly fascinates me. According to the Anaplast engineering source, they don't just leave standard air in there, they vacuum out the air and fill that gap with invisible, noble gases.
Yes, normal air is an okay insulator, but it has flaws. It contains moisture, and more importantly, the oxygen and nitrogen molecules in air are relatively small and active. They conduct kinetic heat energy relatively easily across the gap. By vacuuming out the air and replacing it with a heavier noble gas, you dramatically reduce the thermal conductivity across the window.
I really want to break down how this works. Let's think of these noble gases like a hierarchy of winter coats for your house. If standard air inside an IGU is like wearing a basic thin windbreaker on a freezing winter day, it traps a tiny bit of heat, but the wind cuts right through it and you're still going to feel a deep chill. You are losing body heat fast.
That is a very fair baseline. Convection currents easily form in standard air gaps, physically carrying the heat from the warm inner pane to the cold outer pane.
Then you step up to argon. Argon is the undisputed standard for almost all high-quality IGUs produced today. Argon is like putting on a solid, highly reliable, thick puffer jacket. Arnoplast notes that argon is roughly 30% better at insulating than standard air. It is relatively cheap because it makes up about 1% of our atmosphere, so it's easy to extract.
But we need to explain why it acts like a puffer jacket. Argon has a significantly higher atomic mass than the nitrogen and oxygen that make up normal air. The atoms are larger and heavier. Because they are heavier, they move slower. They're sluggish. Therefore, they are physically worse at transferring kinetic heat energy from one pane of glass to the other. Furthermore, because the gas is denser, it strongly resists forming those convective loops inside the window cavity.
That makes perfect sense. Heavier, slower atoms mean less heat transfer. And Anaplast points out that argon performs at its absolute peak when the physical gap between the two panes of glass is about 12 to 20 millimeters wide. That's the sweet spot for the pucker jacket. It gives you the best bang for your buck.
However, sometimes architects run into physical constraints. In ultra-efficient triple-pane windows or in highly specialized historical renovations, the window frame simply isn't deep enough to allow for two massive 20-millimeter gaps. You might only have space for an 8 or 10-millimeter gap. If you put argon in a gap smaller than 12 millimeters, it loses its effectiveness. There isn't enough volume to stop the thermal transfer. That is where you have to move up the ladder to Krypton.
Krypton is the high-tech, extreme Arctic expedition suit. It is significantly denser and heavier than argon. It provides 10 to 20% better thermal insulation than argon, and its superpower is that it reaches peak efficiency in very tight spaces gaps, around 8 to 12 millimeters. But because it is found in trace amounts in the atmosphere, something like 1 part per million, it is much harder to extract, making it significantly more expensive.
And then, for the absolute no-compromise extreme edge cases of architectural engineering, there's xenon.
Xenon. If argon is a puffer jacket and krypton is an Arctic suit, xenon is the multi-million-dollar, custom-tailored astronaut spacesuit.
Exactly. Xenon is incredibly dense. It offers the absolute highest possible thermal insulation of any gas you can put in a window, achieving the lowest possible U values, meaning the absolute minimum heat transfer. But it is astonishingly rare in the atmosphere and staggeringly, prohibitively expensive to isolate.
Anaplast engineering notes are very clear on this point. They state plainly that for typical residential construction, even for ultra-luxury multi-million-dollar mansions, xenon simply does not justify the immense cost. The return on investment in energy savings would take centuries. It is generally reserved for ultra-high-end experimental architecture, extreme climate outposts, or highly specialized research and medical facilities, where maintaining precise internal temperatures down to the fraction of a degree is a matter of mission success or failure.
So we have the warm edge spacers preventing edge loss. We have the heavy noble gases acting as a sluggish thermal barrier. But we are still missing the final, most crucial piece of the modern window puzzle, the invisible layer that truly turns the IGU into a thermos, low emissivity or low-E coatings.
Low-E coatings. This is where glass engineering crosses into nanotechnology. Let's define the term first. What exactly is emissivity?
Emissivity is simply a measurement of a material's ability to radiate or emit thermal energy. Standard clear, uncoated glass has a very high emissivity. It eagerly absorbs heat energy from a room and then happily radiates it right out into the cold night air. It just lets long-wave infrared heat pass straight through.
Which is terrible if you're trying to keep your house warm in winter or cool in summer. A low-E coating is the solution. It is a microscopically thin layer of metallic oxides, often layers of pure silver, applied directly to the surface of the glass. And when we say thin, we mean practically invisible. We are talking nanometers thick, about 500 times thinner than a single human hair.
It essentially acts as an invisible thermal mirror. In the winter, when you are running your furnace, everything in your house, the walls, the furniture, the air, emits long-wave infrared heat. When that heat hits the window, the low-E coating acts like a mirror, reflecting the heat right back into the living room instead of letting it escape through the glass. In the summer, the process works in reverse. It reflects the sun's scorching exterior infrared heat away from the building, drastically reducing the load on your air conditioning.
And there are two fundamentally different ways the industry applies these metallic coatings. The first is what they call a hard coat, or in technical terms, a pyrolytic coating. And the timing of how they apply this is insane. They actually apply it at the float glass plant, right in the middle of manufacturing. While the ribbon of glass is still 1200 degrees Fahrenheit, floating on the molten tin bath, they spray a chemical vapor of metallic oxides directly onto the hot glass.
And because the glass is in a semi-molten state, the metallic oxides literally bake into and fuse molecularly with the surface of the glass.
Which is why it's called a hard coat. Because it's chemically fused to the glass, it is incredibly robust and durable. You can expose it to the outside elements, you can touch it with your bare hands, you can scrub it with a squeegee, and it won't degrade. But the downside is that it doesn't insulate quite as well as the alternative. And because it is baked into the surface, it can sometimes have a very slight visible haze or tint to it under certain lighting conditions.
The alternative and the standard for high-performance modern architecture is the soft coat. This is applied completely differently. It is applied long after the glass is cooled, using a process called magnetron sputtering inside a massive vacuum chamber.
Okay, stop. Magnetron sputtering inside a vacuum chamber. You just threw an entire sci-fi novel's worth of vocabulary at me. Please, break down magnetron sputtering for me. Explain it like I'm 5.
Let's demystify it. A magnetron is simply a device that generates a powerful magnetic field. It's the same core technology that powers your microwave oven. Sputtering is a physical process. Imagine you take a solid block of pure silver, we call it the target. You put the silver target and the pane of glass into a massive steel chamber, and you pump all the air out to create a deep vacuum. Then you introduce a tiny amount of an inert gas, like argon, and you ignite it into a glowing plasma using high voltage.
So we have a vacuum chamber full of glowing, highly energized plasma.
Exactly. The powerful magnetic field from the magnetron accelerates the ions in that plasma and violently slams them into the solid block of silver. The impact is so forceful that it physically knocks individual atoms of silver off the block. Those freed silver atoms fly through the vacuum and gently land on the surface of the glass, stacking up atom by atom.
They are literally spray painting the glass with individual atoms of metal.
Atom by atom, building highly precise, incredibly complex microscopic layers. Soft coats often consist of multiple alternating layers of silver, zinc oxide, and titanium to achieve exact optical and thermal properties. Soft coats offer vastly superior thermal performance, incredibly low emissivity, phenomenal heat blocking, and flawless optical clarity with no haze.
But, as the name implies, the soft coat is extremely delicate. Because it was gently laid down atom by atom at room temperature, it is not fused to the glass. You cannot touch it. If you run your finger across it, you'll wipe the coating right off. Furthermore, if the pure silver layers are exposed to ambient air and humidity, they will rapidly oxidize. They will tarnish and turn black, just like old silverware.
Which dictates exactly how the window is built.
Yeah.
Soft coats can never be exposed. They must always be facing inward, safely permanently sealed inside the dry, noble gas-filled cavity of the IGU.
And the specific placement of that delicate coating inside the IGU is a highly strategic decision for architects. Let's orient ourselves. The industry numbers the surfaces of the glass panes from the outside of the building moving inward. Surface 1 is the physical glass facing the street where the rain hits. Surface 2 is the inside of that outer pane facing the argon gas cavity. Surface 3 is the inside of the inner pane also facing the gas. And surface 4 is the glass you can touch from inside your living room.
So, assuming a standard double pane IGU, you have two safe surfaces inside the cavity, surface 2 and surface 3. Where you place the soft coat depends entirely on your local climate.
Let's do a scenario. Let's say you are building a house in a scorching, cooling-dominated climate like Phoenix, Arizona, or Miami, Florida. Your main enemy is the sun's radiant heat entering the house.
In a hot climate, you absolutely want the low-E coating placed on surface 2, the inside of the outer pane. As the sun's intense radiant heat hits the window, the coating intercepts it immediately and reflects it back outside before it can even cross the argon gas cavity. It stops the heat at the first line of defense, drastically lowering your air conditioning costs.
Okay, flip the scenario. You are building a cabin in a freezing, heating-dominated climate like Minneapolis, Minnesota, or Anchorage, Alaska. Your enemy is not the sun. Your enemy is your expensive furnace heat escaping into the winter night.
In a freezing climate, you want the low-E coating on surface 3, the inside of the inner pane. Now, the coating is acting as a thermal mirror facing the interior of the house. When your furnace pumps warm air into the room, that long-wave infrared heat tries to escape through the window. It hits surface 3, and the coating aggressively bounces that heat right back into your living room, keeping you warm and lowering your heating bills. Furthermore, putting it on surface 3 allows the short-wave, warming rays of the winter sun to enter the house, providing free, passive solar heating.
It is all about managing two critical metrics. The U value, which measures non-solar heat transfer, how well the window acts as a blanket, and the solar heat gain coefficient, or SHGC, which measures how much of the sun's direct radiant heat is allowed through the glass. By combining different gases, warm-edge spacers, and strategically placed atom-thick silver coatings, engineers perform a highly tuned balancing act to make massive glass skyscrapers more energy efficient than solid walls used to be.
It is a phenomenal achievement in material science.
All right, let's shift our focus from the standard building envelope and the pursuit of energy efficiency and move into the extremes. We are entering Section 4, Specialty Glass. We're talking about glass designed for fire, frost, and the absolute magic of electro-responsive smart glass. Let's start with extreme life-threatening heat. Fire. We mentioned earlier that normal annealed glass shatters at around 250 degrees Fahrenheit due to thermal stress. Tempered glass can hold out until about 500 or maybe 600 degrees before losing its temper and shattering. But in a full-fledged commercial building fire, temperatures can easily flash over and exceed 1,500 degrees Fahrenheit in minutes.
Standard glass will utterly fail in those conditions, creating pathways for oxygen to feed the fire and allowing smoke and toxic gases to flood escape routes, which is where specialized fire-rated glass becomes a literal life-saving necessity. The CM Tech Guide divides this complex field into two distinct categories, fire protective and fire resistive. They sound incredibly similar to a layperson, but legally, functionally, and chemically, they are vastly different beasts.
Let's break them down. Fire protective glass is exactly what it sounds like. It is designed to be a physical barrier. It holds back the flames and the deadly smoke. It keeps the fire localized in one room, preventing it from immediately spilling into the hallway where people are trying to evacuate. We're talking about things like the old school, heavy polished wired glass you see in old schools, or modern, highly advanced clear glass ceramics that have essentially zero thermal expansion and can physically survive the brutal 1,600-degree heat of a raging fire while being blasted with cold water from a fire hose without shattering.
The ceramic structure is incredible,
Yeah.
but fire protective glass, by definition, has a massive, potentially fatal vulnerability in certain architectural scenarios. It blocks the flame and it blocks the smoke, but it does absolutely nothing to stop radiant heat.
Radiant heat. Explain the danger there.
If a massive fire is raging on one side of a fire protective window in a corridor, the physical glass will stay intact. The flames won't touch you. But the intense radiant energy passing straight through that clear glass can be so staggeringly hot that objects on the other side of the hallway, paper, curtains, furniture, or, tragically, people trying to escape, can spontaneously combust or suffer severe, life-threatening burns without a single lick of flame ever crossing the barrier. The heat transfer is lethal.
That is terrifying. So here's where the engineering gets really interesting. To solve that invisible radiant heat problem, we have to move to the second category, fire-resistive glass. And this isn't just a thicker piece of glass or a different recipe of sand. It is an active, multi-laminated, chemically engineered unit. It is built with alternating layers of glass and a very special chemical called an intumescent.
Intumescent technology is a brilliant application of passive chemical safety systems. These intumescent layers are often made of hydrated sodium silicate. Under normal, everyday room temperature conditions, these layers are perfectly clear. The window looks like any normal, thick pane of architectural glass.
But when exposed to the massive, terrifying heat of a building fire, they undergo a violent physical and chemical transformation. Let's walk through the mechanics of a fire hitting this glass.
The fire breaks out. The temperature spikes. The first layer of glass facing the fire heats up and eventually shatters from thermal shock. But it stays adhered to the intumescent layer behind it. Now that extreme heat hits the chemical intumescent layer. The heat causes the water molecules trapped within the sodium silicate to rapidly boil.
And as the water boils and turns to steam, it triggers the chemical to violently expand and foam up. It puffs up, multiplying its thickness several times over, turning completely, solidly opaque white.
It physically transforms, in real time, from a clear optical layer into an insulated, highly refractory heat-blocking brick wall right inside the glass unit. The expanding foam absorbs massive amounts of thermal energy. As the fire continues to rage, the process moves through the subsequent laminated layers, one by one, creating deeper and deeper insulation.
The result is mind-bending. You could have a 1600-degree inferno raging on one side of the glass, melting the metal framing, and you could practically press your bare hand against the glass on the safe side of the corridor and not get burned. It blocks the radiant heat completely, providing a safe, cool passage for evacuation.
It is chemistry saving lives in real time. Now, obviously, not all specialty glass is designed for apocalyptic life and death situations. Sometimes we manipulate the surface of the glass simply for privacy, light diffusion, or aesthetic design.
Right. Moving from fire to frost, the world of decorative glass. If you want a frosted window for a bathroom or an office partition, you have a few ways to do it. You've got your acid-etched glass. This involves treating the surface of the glass with highly corrosive hydrofluoric acid. The acid eats away microscopic layers of the silica, creating a remarkably smooth, satin-like, permanent frosted finish that diffuses light beautifully and resists fingerprints.
If you need deeper texture or custom patterns, you use sandblasted glass.
Yeah.
This is exactly what it sounds like. High-pressure air blasts aluminum oxide or sand at the glass, physically chipping away microscopic pieces of the surface. It allows for highly precise, intricate frosted patterns to be carved into the glass using stencils.
And then there's the ultimate fusion of art and durability, ceramic frit. This process fascinated me because it's so permanent. It involves taking finely ground, microscopic glass particles mixed with inorganic colored pigments, the frit. You print this mixture onto the surface of the glass. You can use traditional silk screening for repeating dot patterns, or even massive, specialized direct-to-glass digital inkjet printers to print full-color, high-resolution photographs or complex artwork directly onto the pane.
But the ink is just powder at that point. The magic happens next. The printed glass is sent into the tempering furnace. As the glass reaches that 600 or 700 degrees Celsius required for tempering, the powdered ceramic frit actually melts and fuses permanently into the molecular structure of the base glass.
It becomes one unified material. The color is permanently baked in. Because it is physically part of the glass, it will never peel, it will never scratch off under normal conditions, and it is completely impervious to fading from UV light. Architects use it all the time to control solar glare on building facades, or increasingly to print highly specific patterns that are visible to birds but mostly transparent to humans, dramatically reducing bird strikes on modern skyscrapers.
But the absolute coolest, most futuristic, decorative, and privacy technology on the market today has to be smart glass, also known as switchable or dynamic glass. This is glass that can literally change its optical properties, from clear to opaque, or dynamically changing its tint with a simple flip of a wall switch or a command from an app.
It feels like magic every time you see it. According to the engineering deep dive from Tough Glaze, there are a few entirely different ways to achieve this, relying on very different principles of physics. Let's start with the most common one, which Tough Glaze notes holds over 95% of the privacy glass market. PDLC, or polymer dispersed liquid crystal. Break down the mechanics of PDLC for me.
It relies on the unique properties of liquid crystals, specifically nematic liquid crystals. Inside the laminated glass sandwich, between two layers of conductive coating, you have a polymer matrix. Suspended within this matrix are millions of microscopic droplets containing these liquid crystals.
Now, when the system is resting, when the power is completely turned off, What are those crystals doing?
When the power is off, the liquid crystals are completely unorganized. They're pointing in every random direction imaginable. Because their orientation is chaotic, when light hits the glass, the light waves hit those crystals, refract, bounce around, and scatter in every direction. The scattered light cannot form a coherent image. Therefore, to the human eye, the glass looks solidly frosted, a milky, opaque white. It provides total privacy.
But when you hit the switch, you apply an alternating electrical voltage across those conductive coatings. What happens to the chaotic crystals?
The electrical field forces those microscopic liquid crystals to instantly snap to attention. Like tiny magnetic compass needles responding to a powerful magnet, they all align perfectly parallel to one another and parallel to the direction of the light. Because they are aligned, the light waves can pass straight through the gaps between them without scattering.
The glass goes from completely frosted opaque to brilliantly clear in milliseconds. Turn the power off, the electrical field drops, the crystals randomize, and it instantly goes back to opaque. It is a stunning visual effect.
It is excellent for instant privacy in conference rooms or hospital ICUs. However, PDLC is binary. It's either clear or opaque. It doesn't actually block much solar heat, it just diffuses the light. If you want to dynamically control the sun, you need a different technology, SPD, or suspended particle device.
How does SPD differ?
Instead of liquid crystals, SPD uses millions of microscopic, rod-shaped, light-absorbing particles suspended in a liquid film between the glass panes. When the voltage is off, the particles are randomly dispersed. But because they are light-absorbing, they don't turn the glass milky white. They aggressively absorb the light, tinting the glass a very dark blue or almost black, blocking up to 99% of the light and significant heat.
When you apply the voltage, the rod-like particles align, letting light through, and the glass clears up. And the major advantage over PDLC is that SPD isn't binary. You can use a dimmer switch. By modulating the exact voltage, you control exactly how many particles align, meaning you can precisely dial the tint level up and down to match the glare of the sun. It is heavily used in the panoramic sunroofs of high-end luxury cars and yacht windows.
And finally, there is the heavyweight of the smart glass world, electrochromic glass. This technology doesn't use liquid crystals or physical suspended particles at all. It uses a complex reversible chemical reaction. It relies on the migration of lithium ions between microscopic ceramic thin film layers inside the glass, triggered by a very low DC voltage.
Because it is physically moving ions back and forth to trigger a chemical color change, it is a much slower transition. It doesn't snap clear in milliseconds. It can take several minutes to fully tint from clear to dark, like a slow-moving cloud passing over the sun.
But it has a massive energy advantage. With PDLC or SPD, you have to constantly supply electricity to keep the glass clear. The moment the power cuts, they default to opaque or dark. Electrochromic glass is the opposite. It requires a tiny jolt of power to change its state, but once the ions have migrated and it is tinted, it requires virtually zero power to maintain that state indefinitely. It's often used in the facades of massive commercial buildings or airplane windows, like the passenger windows on the Boeing 787 Dreamliner. The passengers have a button to slowly dim their window, managing the intense high-altitude daylight and heat without needing physical plastic blinds that break or get dirty.
Speaking of applying electricity to glass, I want to take a quick, highly entertaining historical detour that the CM Tech source brought up in their materials because it blew my mind. We think of electrically active glass as a 21st century invention. But in 1974, Ford released an option called the DW825 Quick Defrost Windshield on the Thunderbird and the Continental Mark IV.
Yes. The infamous gold film windshield.
Yeah.
An incredible piece of over-engineering.
They literally engineered a transparent, genuine gold-bearing metallic film and embedded it directly inside the PVB plastic interlayer of the laminated windshield. The driver would hit a massive toggle switch on the dashboard, dump a colossal amount of electricity into the gold film, and the resistance would cause the entire windshield to rapidly heat up. It would melt thick winter ice and frost 5 times faster than standard blowers. It was completely silent space-age tech.
But as an automotive option in the mid-70s, it was wildly comically impractical.
Utterly. The option cost $306.70 in 1974, which, adjusted for inflation, is roughly $2,000 today just for the privilege of having the button. Because it had actual gold in it, if a rock broke the windshield on the highway, it cost an absolute fortune to replace. And the electrical draw of heating a massive piece of laminated glass with 1970s technology was so violently high that the car literally required a heavy-duty 100-amp second alternator installed in the engine bay just to power the windshield without stalling the car.
It was a commercial failure and quietly disappeared. But if we connect this historical oddity to the present day, that exact fundamental concept is experiencing a massive vital resurgence.
And it's entirely because of the rise of electric vehicles.
Precisely. Let's look at the thermodynamics of a car. In a traditional internal combustion engine car, the engine is essentially a controlled explosion. It generates massive amounts of waste heat. When you need to defrost your windshield in the winter, the car just redirects some of that free, abundant waste heat via a blower fan onto the glass. It costs you nothing in terms of fuel efficiency. But an EV does not have a hot engine block. Electric motors are incredibly efficient and run cool.
So if you want hot air to blow on the windshield in an EV on a freezing morning, you have to run a dedicated resistive electric heater, like a giant hairdryer. And that heater drains electricity directly from the main high-voltage battery, the same battery you desperately need to actually drive the car.
Which is a massive problem. Blasting an electric heater to clear a windshield can severely, dramatically reduce an EV's driving range in the winter. So, modern automotive manufacturers have reached back to 1974 and revived the heated windshield.
But they aren't using gold and secondary alternators anymore. Modern heated windshields use completely invisible, wafer-thin, conductive silver coatings sputtered inside the glass, similar to the Lowy soft coats we discussed. When powered, the invisible silver layer heats the massive pane of glass directly, uniformly, and highly efficiently. It effortlessly melts ice and prevents fogging without the need to run an energy-hungry air blower, ultimately saving precious battery range and extending the winter capability of the vehicle.
It is amazing how a 50-year-old failed ultra-luxury vanity feature is now a critical foundational efficiency technology for the future of transportation.
And speaking of efficiency and the future, that brings us to the next massive phase of our deep dive. Because this entire industry, as incredible as the chemistry and the engineering is currently staring down a massive existential challenge. We turn now to the 2026 report from the Glass Manufacturing Industry Council, or GMIC. Let's set the stakes. The glass industry is an absolute economic juggernaut. According to the data, it is projected to reach $202.37 billion globally by 2026. The demand is skyrocketing across every sector. We need billions of square feet of architectural glass for megacities, complex curved automotive glazing for new car designs, ultra-clear glass for solar panels, and there is a massive resurgence in demand for infinitely recyclable container glass as the world desperately tries to move away from single-use plastics.
Wow. The demand is higher than it has been in human history. But here is the existential problem. As we discussed in length earlier, manufacturing glass from raw materials requires melting rocks at 1500 degrees Celsius 24 hours a day, 365 days a year. It is an incredibly, relentlessly energy-intensive process. According to the GMIC data, conventional glass production is responsible for roughly 2.6% of total global industrial CO2 emissions.
2.6%. When you look at the scale of global industry, that is a staggering amount of carbon entering the atmosphere just to make windows and bottles.
Which raises perhaps the most important question of this entire deep dive. How does a 3,000-year-old, fundamentally high-heat, heavy industry survive, let alone thrive, in a low-carbon, highly regulated future? The status quo is mathematically and environmentally unsustainable.
The answer, according to the industry leaders and the GMIC report, lies in rapid, aggressive innovation in the near term and pure sci-fi leaps in the far term. Let's start with the near-term revolution. The target is the heart of the beast, the furnace. The GMIC notes that major manufacturing companies are aggressively, actively moving away from the standard, massive natural gas-fired furnaces that have defined the industry for a century. We are finally seeing commercial-scale hybrid and fully electric melting furnaces coming online.
The transition is happening now. Libby, one of the largest glass makers in the world, is currently executing a massive infrastructure overhaul in Ohio. They are tearing down 4 older, highly emissive fossil fuel furnaces and replacing them with 2 state-of-the-art hybrid electric furnaces. Their engineering target is to slash their carbon emissions by 60%. Over in Europe, the container glass giant Ardagh Group recently fired up a hybrid furnace in Germany that operates using 60% renewable electric heating. The results are already proven. They are reducing carbon emissions by 64% per glass bottle produced. And the single furnace saved over 35,000 tons of CO2 from entering the atmosphere in its very first year of operation.
It's incredible progress, but it's not just the heavy hardware, it's the software running the plant. The industry is rapidly deploying artificial intelligence to squeeze every single possible drop of thermodynamic efficiency out of these massive facilities. AI systems are monitoring the complex sensor arrays inside the furnaces in real time. The AI constantly analyzes and adjusts the oxygen to fuel mixtures hundreds of times an hour to ensure perfect, complete combustion, dramatically cutting heat waste. AI predictive maintenance algorithms analyze thermal imaging to detect microscopic weaknesses in the furnace refractory bricks, preventing catastrophic heat loss or unexpected shutdowns.
And perhaps most visibly on the factory floor, AI is running high-speed machine vision cameras. These cameras inspect the continuous ribbon of float glass moving at high speeds, detecting microscopic bubbles, seeds, or distortions in the glass that human eyes would miss. The AI instantly marks the defects so the automated cutting machines can optimize the cuts around them, drastically reducing the amount of good glass that gets scrapped and thrown back into the furnace to be remelted.
And speaking of throwing glass back into the furnace, AI is completely revolutionizing the recycling side of the equation, too. We mentioned cullet earlier. Cullet is simply recycled, broken glass of the same chemical recipe. Cullet is the secret weapon for decarbonization. Why? Because cullet has already been melted once. The intense chemical reactions that require massive energy have already happened. Melting cullet requires significantly, dramatically less thermal energy than trying to melt raw sand, soda ash, and limestone from scratch.
It is the easiest win in the industry. But historically, the problem has been quality control. If you accidentally mix green glass cullet into a batch of clear glass, or if a piece of ceramic coffee mug gets into the cullet stream, it can ruin an entire multi-ton batch, causing massive losses. AI-enabled optical sorters at advanced recycling plants are solving this. These machines use high-speed cameras and air jets to instantly identify and separate crushed glass by color and chemical composition as it flies off a conveyor belt. They provide incredibly pure, reliable cullet to the manufacturers. The GMEC notes a simple but profound statistic. For every 10% increase in cullet usage in a furnace batch, a manufacturer achieves a direct 3% energy savings and cuts their CO2 emissions by 7%.
So that is the near term. Electric furnaces, AI optimization, and supercharged recycling. It's practical, heavy industry progress. But the architectural engineering source, Tough Glaze, gives us a breathtaking peek at the far-term innovations currently emerging from laboratories. The stuff that sounds like pure science fiction, but has already been proven in prototypes. First up, transparent solar panels.
We have been dreaming about this for decades. Specifically, researchers are perfecting Grätzel cells, also known as dye-sensitized solar cells. Traditional silicon solar panels are opaque, heavy, and black. Grätzel cells work more like artificial photosynthesis. They use a microscopically thin, light-absorbing dye applied to a transparent conductive oxide layer on the glass. When sunlight hits the dye, it excites electrons, which are then channeled away as electrical current.
And the incredible part is that they can convert visible light into electricity while remaining largely transparent to the human eye. They might have a slight tint, but you can see right through them. The proof of concept is already out there. The Copenhagen International School in Denmark has a facade covered in 12,000 of these specific tinted energy-generating glass panels. Imagine a near future where every single glass window on a 100-story skyscraper in Manhattan is silently, passively generating megawatts of clean power for the building's electrical grid just by sitting in the sun. It turns the building envelope from an energy drain into a power plant.
It is a paradigm shift in urban energy production. Then there is the pursuit of flexible glass. I know we spent a lot of time earlier talking about Gorilla Glass and how incredibly hard and rigid it is, but material scientists are breaking the rules. They're engineering glass that actually bends.
Which feels wrong on a fundamental level. Glass snaps.
Conventional silica-based glass snaps because any applied stress concentrates at microscopic surface flaws until the bonds break. But Corning developed Willow Glass by creating glass that is unimaginably thin, roughly the thickness of a human hair, and using advanced manufacturing techniques that eliminate absolutely all surface flaws, the glass can actually bend, flex, and be rolled up onto massive spools like sheets of paper or plastic film.
And the university researchers are pushing it even further. A team at the University of Lyon in France has been working with an entirely different chemical base. They discovered an aluminum-based glass structure that behaves molecularly more like a ductile metal than a brittle ceramic. It can actually be physically stretched and deformed at room temperature without breaking.
The commercial goal for this technology is massive. We are talking about true folding tablets, smartphone screens that wrap around your wrist like a bracelet, and highly durable, flexible displays woven into clothing. The glass material itself is practically ready. The industry is honestly just waiting for the flexible batteries and silicon chips to catch up to the glass.
There's also a massive industry-wide push for lightweight glass. Architectural glass is incredibly heavy. A standard 10-foot window pane requires cranes and heavy machinery to install. By altering the atomic structure, utilizing materials like titanium and zirconium in the batch, manufacturers are producing structural architectural glass that is 30% lighter and requires 70% less energy to produce than the standard float glass of 50 years ago. This is huge for reducing the deadweight of skyscrapers and drastically slashing the diesel fuel costs of shipping these heavy panels around the world.
And finally, perhaps the most wildly sci-fi concept of them all, currently being explored by advanced material science teams: self-healing glass.
Okay, self-healing concrete, I understand. The ancient Romans figured that out using volcanic ash and quicklime. Water hits a crack, it reacts and seals the fissure. But glass? A crack in a rigid, amorphous solid like glass is a permanent, catastrophic failure of the molecular bonds. How do you heal that?
Historically, you couldn't. It was permanent. But a joint team of scientists in Israel and North America made an incredible discovery. By synthesizing a specific peptide, a short chain of amino acids, the building blocks of proteins, and mixing it with simple water solvent, they were able to induce a process called molecular self-assembly.
Wait, they were using biological building blocks to make glass? Essentially, yes. The peptides spontaneously organize themselves into a rigid, highly ordered, completely transparent glass-like material. It is clear, it is incredibly strong, and here is the miracle. Because the structure is formed by non-covalent biological bonds, if the material sustains a microfracture or a crack, the chemical structure naturally, autonomously realigns and repairs itself over time, especially in the presence of minor humidity. The crack literally zips itself back together at the molecular level.
It's mind-blowing. It completely redefines what a solid material can be. But as we look at all this incredible technology, the AI-optimized electric furnaces, the 10,000 psi tempering processes, the multi-layered smart glass, the transparent solar cells, we have to confront a harsh reality. None of this technology matters. None of these sci-fi innovations will ever scale or see the light of day without the human element. Which brings us to the final and most critical phase of our deep dive: the workforce gap, and specifically what this means for your personal growth potential. Both the GMIC Industry Report and the CM Tech Crash Course highlight a severe impending crisis that the industry is aggressively trying to solve. The glass industry and the advanced manufacturing sector as a whole is facing a massive structural labor shortage.
The demographic numbers are incredibly stark and sobering. Just looking at the wider skilled trades that support manufacturing and installation, the data shows we are seeing roughly 10,000 highly experienced master electricians retire every single year. But only 7,000 new apprentices are entering the field to replace them. That is a net loss of 3,000 skilled professionals every single year. And when you zoom out to the broader manufacturing sector, reports project a staggering shortfall of up to 2.1 million skilled workers required by 2030 to keep the economy running.
The generation of highly skilled craftsmen and engineers who built the infrastructure of the 20th century is retiring. They are taking their institutional knowledge with them. And the technologies we have discussed today in such intense detail, calculating the thermal loads of noble gases, managing AI-driven electric furnaces, seamlessly integrating transparent solar cells into a smart city grid, or executing the flawless installation of structural silicone glazing on a 100-story skyscraper, these tasks cannot be automated away. They require a human workforce that is highly skilled, remarkably adaptable, and deeply knowledgeable about both the theory and the physical craft.
So we arrive at the ultimate question. What does this all mean for you, the listener? Why did we spend the last hour taking you deep into the molecular structure of molten sand and the physics of tempering? It means that this industry, and honestly the global technical economy as a whole, desperately needs people who can bridge the immense gap between the complex theoretical science we've discussed and the practical, boots-on-the-ground reality of making it, optimizing it, and installing it safely.
And it is absolutely crucial to understand this next point. What will make you truly great, truly indispensable in this field, or frankly in any advanced manufacturing, engineering, or technical field, is not your ability to act as a human encyclopedia. It's not your ability to memorize static facts and figures. You do not need to memorize the exact melting point of pure silica, or the atomic weight of krypton, or the tensile strength baseline of heat strength in glass.
Exactly. You have a smartphone. You have AI. You can look those numbers up in 5 seconds. What you cannot look up, what an AI cannot simulate, Fenor, is critical thinking. The foundation of true lasting success in this rapidly evolving environment is cultivating a relentless growth mindset. It is the willingness to walk onto a factory floor, look at a process that has been done the exact same way for 50 years, understand the physics behind why it works, and then have the courage to ask, how can we do this better? How can we reduce the carbon footprint of this step? How can we make this safer for the operators?
It is about an insatiable curiosity and a commitment to constantly learning new skills. Maybe your journey starts right here by understanding the foundational basics of the float glass process. But a growth mindset means you carry that curiosity forward. You realize that the principles of microscopic thin-film metallic coatings applied via magnetron sputtering on Lowy glass are highly, directly applicable to advanced optics, laser manufacturing, and the semiconductor industry that builds computer chips.
Everything is connected. Understanding the kinetic thermodynamics and convection loops inside an insulated glass unit translates beautifully into broader mechanical engineering, HVAC system design, and the massively expanding field of sustainability and green energy management.
Or perhaps your growth takes you away from the raw science and into the critical realm of leadership. Using this deep technical foundation to develop the human management skills necessary to run an advanced AI-assisted manufacturing floor, or coordinating the hyper-complex logistics and safety protocols required to execute the installation of a massive, structurally glazed curtain wall hanging hundreds of feet above a crowded city street. The specific technical details of the machinery will always evolve and change, but your ability to learn rapidly, to adapt to new paradigms, to think critically through complex problems, and to lead a team effectively, those skills are permanent and universally valuable.
As we prepare to wrap up this massive deep dive, there is a vital grounding perspective that we need to leave you with. When we talk about glass, it's easy to get lost in the aesthetics. But as climate change continues to rapidly drive more extreme, volatile, and unpredictable weather patterns across the globe, glass is no longer just an aesthetic architectural choice.
It is absolutely not just about making a corporate headquarters look pretty, shiny, and modern.
Exactly. Glass is the crucial, invisible, frontline shield keeping our homes, our hospitals, and our workplaces habitable. It is the highly engineered, multi-layered barrier responsible for maintaining safe, comfortable, life-sustaining temperatures inside, even when the outdoors are unbearably dangerously hot, freezing cold, or battered by severe destructive storms. The innovations happening right now in the glass industry are directly impacting human survival, energy conservation, and comfort in a rapidly changing climate. The stakes are incredibly high.
And the organization that produced this custom, highly detailed deep dive for you asked us to deliver a direct, earnest, and personal message as we close. They believe deeply, fundamentally, in your potential. They would not invest the significant time, the energy, and the extensive resources into creating highly specialized, complex educational deep dives like this if they did not believe, without a shadow of a doubt, that you are truly capable of learning, mastering, and ultimately advancing this field, and whatever other incredible fields you choose to explore in your career.
The massive challenges of the 21st century, from decarbonizing heavy industry to building resilient infrastructure, require capable, curious, and dedicated minds. They know you have that capability, you just have to apply it. We want to leave you with one final, provocative thought to mull over today. We started this hour by talking about that invisible barrier, that frozen, chaotic dance floor of atoms that you look right through every single day without noticing. I want you to look at the nearest window right now. Imagine a future, not too far from this exact moment, where the glass in your home isn't just a dumb, passive barrier to the wind.
Imagine it as a highly complex active intelligence, a dynamic membrane, generating its own clean power from the sun, silently repairing its own microscopic fractures, and autonomously adapting its tint and thermal insulation to the shifting, chaotic weather outside in real time, all to keep you perfectly safe and perfectly comfortable.
That sci-fi future isn't a dream. It is actively being built in laboratories and factory floors right now, and it desperately needs people exactly like you to step up, learn the science, and bring it across the finish line into reality. We wish you the absolute best of luck and boundless success on your ongoing learning journey. Keep asking the hard questions, keep unpacking the complex world around you, and as always, keep diving deep.